それでは続きましてのプレゼンターご紹介させていただきましょう。ディエゴ・キングストンさんです。We'd like to invite our next speaker, Mr. Diego Kingston. Yeah, Mr. Kingston, the floor is yours.
ありがとうございました。皆さんと一緒に、大阪にいてとても嬉しくて光栄です。Excuse me, I am now going to give the presentation in English, but I hope that sometime I will be able to do it in Japanese. So my talk is going to be about the future of zkVMs and especially about post-quantum signatures in Ethereum, which is one of the current threats we are facing. And so I wanted to talk a little bit about some design choices or trade-offs and some of the recent developments that we have seen. So this is a bit the outline of my talk. I am going to first mention some of last year's advances, then comment a little bit on the quantum threat, why this is important for Ethereum, then a little bit about the different signature candidates, also then talk a little bit about these multilinear versus univariate Starks. So these last few years there was a discussion between using snarks or Starks. It now seems that this discussion is settled. And then we have to choose maybe which is the right way to encode them with polynomials. Maybe we can have both. And then some design choices, and finally a little bit about why build a different VM, especially for what is signature aggregation, what advantages this can give us. And I'll finish with a short summary of what we have been talking. So some of last year's advances. First, we saw that we have very powerful, transparent validity proofs. That is, proof systems that don't rely on a trusted setup such as Groth16 or KZG Plonk. Okay, and this has several advantages, and we don't have this point of failure. So this is something interesting. Then we saw that we have general purpose zkVM that allow us to prove code written in Rust. And these have become really powerful. In fact, it's been shown that we can prove over 200,000 Poseidon 2 hashes per second, or even more. That depends on your hardware, but this shows that we can prove enough hashes for what is practically meaningful for Ethereum. Then we saw the emergence of real-time proving. Right now, I think we have 3 or 4 zkVMs that can do this, and we can expect that they will get better and better. Besides, power consumption has been going consistently down, and so perhaps it will be possible for us to prove things directly from home and not from a GPU farm. There has been a lot of developments related to hardware acceleration. NVIDIA has also added in its library the instructions for example, Poseidon 2 and other primitives that are useful for proof systems. We have seen a lot of better new lookup arguments, especially lookup and GKR. We also have new ways of arithmetization, and that gives us more flexibility to describe our VM, and then we have also more precise specifications. So what about the quantum threat? The idea is that quantum computers have an efficient algorithm that allows us to break the cryptographic problem that elliptic curves rely on, which is the discrete log. Okay, and basically this breaks all the cryptography, easy cryptography that Ethereum uses, particularly BLS signatures, which are used in the consensus. And this is something that is very unfortunate because these signatures are really powerful because we have very fast aggregation and the verification is rather efficient, and besides, these signatures are very small, so it's very easy to communicate them between the peers. So this also breaks all the elliptic curve-based NARCs, for example, Grok16, which is, again, the proofs are very small, and so we will have to handle like larger proofs. On the other hand, the security of hash functions is reduced, okay, but this is not as catastrophic as the case of elliptic curves, and we can always restore these by working with larger digests. That is to say, if we double the digest, we get back to the security level we had. So why is this important for Ethereum? First, because if this appears, then this can break completely a great part of the cryptography we're working on. But even though this could never happen, I think it's always good to have Ethereum working with cryptography that is as robust as possible, because that makes us resilient against any kind of threats. Besides, we know that Ethereum has already accepted zk as the best strategy for scaling Ethereum. zk is really cheap and fast right now, so it doesn't make sense to have optimistic rollups because the cost of adding zk is negligible. And besides, having zk greatly simplifies the whole protocol because we can essentially verify just these proofs and then just update the results because we know they are correct. Okay, so the execution is basically offloaded. So the thing is, they are going to break our signatures, and so we have to replace them for something else. So there are a couple of things we would like to have. First, of course, we want them to be post-quantum secure. Then we want as minimal and as robust security assumptions. So, for example, hash functions are among the best known cryptographic primitives, so they are a natural candidate. There are other primitives that could also be candidates, but maybe they have like weaker security assumptions, or stronger in this case. Then we would like to have like fast proving, because that way we can use zk to bundle and prove lots of things. We want small proof sizes because that way we can communicate them in the consensus very easily. We would also like the proving to be done in consumer-grade devices because that increases the decentralization, and especially we would like no trusted setups and no need to update the keys during lifetime. So there are a couple of post-quantum signature candidates. We have XMSS, which is hash-based, but this is a stateful signature scheme. Then we have Falcon, for example, that works over lattices. Crystal dilithium also works over lattices. That is, for example, something that FHE uses. And also Sphinx, which is also hash-based but stateless. So the idea is that these signatures aren't aggregatable, but what we can do is use zk to take a bunch of signatures and generate a proof that we verify them. And then just by verifying that proof, it is as if we had verified all the signatures. Okay, and that way we can aggregate. The only problem is that, okay, this solves the problem partially, but doesn't have this nice property that the VLS signature aggregation had, which was insensitive to the order of the signatures. So basically an idea of how XMSS works, because this could be the best candidate. This is because it's based on hash functions, and we know that we can prove hashes with VMs really fast. So the idea is that the signer has a long sequence of one-time public keys, and he builds a Merkle tree with that. And in order to sign, he's going to use one secret key and show the public key is contained in the Merkle tree. So we give like the public key and an authentication path. Each public key is related to a secret key by performing a number of hashes. And the idea is we are going to encode the message using something called incomparable encodings. Then each chunk is going to be interpreted as a number, and that is the number of times we will have to hash the secret key. Okay, and then the idea is that the verifier can check that this is correct by hashing the remaining number of times until he gets to the public key. Of course, when we are doing aggregation and everything, we have to be careful about using the hash function for signing and then for simulating the random oracle. If you want, you can check this paper that explains like all the implementation and all the subtleties. It's really interesting. So now we have to see, okay, we're going to aggregate using these Starks. And so we have like basically two flavors. In one case, we use ordinary polynomials. The idea is that in general, this is what, for example, SP1, RISC-0, ZISC were using or are using. But basically, the idea is we want to prove that the computation is correct, and this is reduced to a claim about certain polynomial equations that have to be enforced over some table. In this case, we have certain freedom to choose the finite field where we are going to work on, but we need it to be something called FFT friendly. And then the idea is basically we get each column of this trace table, we interpolate it using the FFT, we commit to each of these columns, and then basically what we do is we plug in these polynomials inside the constraints that we want to enforce. And then what we do is we divide by a polynomial saying where the constraints should be enforced. Okay, and to show that the constraints are then enforced, we do a low degree testing, okay, and this is the case of Fry, and we generate a proof containing several Merkle trees and everything. So this is a very fast and efficient construction, but in general, this tends to yield larger proof sizes because we have to interpolate each column separately, and we would like perhaps something a bit more efficient. On the other hand, multilinear Starks in general offer more chances for efficient arithmetizations. For example, there are ones using R1CS, but also AIR, which is one of the candidates for a special VM, or M3. So you have like a lot more freedom. We also have a bit more freedom regarding the finite field. The idea is here we use multivariable polynomials, and what we do is we get all the trace and we interpolate it just as one polynomial, not every column. And then the idea is we are going to use this efficient sum check protocol to show that the constraints are enforced. And essentially what the sum check does is transforms this claim to an evaluation of this polynomial at a random point. Okay, and then what we can do is use a PCS to show that the evaluation is correct. Okay, this is a standard technique corresponding to what's called the BCS compiler. So it's interesting that we can use two techniques combined to yield very fast provers and at the same time small proof sizes. Spartan is particularly efficient. So in general, what we want to prove is something like the product of a matrix times a vector is equal to something. And so the idea is you can split it as a claim over some random linear combination over the columns, and then this random linear combination over the rows, and this is particularly efficient. Then WIR is a bit more efficient than Fry because it works over a variant of Reed-Solomon codes that are constrained, and so the idea is that we impose over the witness some conditions. And the idea is that WIR again uses a partial sum check and then does some folding and reduces all the claims. And this way, we get smaller proofs than in the case of univariate Starks. Something that they released a few days ago was also BNews64, that is using a different polynomial commitment scheme, but has been used to prove aggregation of XM SS signatures, and it shows to be very efficient even in CPU. So it's interesting that we have a lot of research and implementations relying on different primitives. So if I had to sum up some of the differences between multilinear and univariate, in general, multilinear have gotten like way popular because of like some advantages. For example, in the case of the sum check, we don't have to calculate like inverses or anything. In general, with multilinears, we can handle better sparsity patterns, and so not have to pay for the zeros contained in the matrix. We don't need to interpolate using the FFT. And in general, because we can use WIR, we can have shorter proofs, and we also have like more options regarding efficient arithmetization or even the use of binary fields. As for the VMs, the idea is that, of course, we have different choices regarding the instruction set architecture, whether it's customized or RISC-V, whether we will have like one table or several tables, what finite field, koala bear, baby bear, the hash function, Ketchak, or the less battle-tested Poseidon 2, whether we're going to use circuits or lookup-based arguments. For example, in the case of Jolt, that's very easy to audit, the arithmetization, the memory argument, the PCS. The good thing is that if we do it like very modular, then we can easily switch one component for the other, where we are going to have a recursive prover or a streaming prover to keep memory bounded. But in the end, I think we will need more than just one design, especially when it comes to execution, to avoid any catastrophic bugs, because these general purpose VMs tend to have like very large and complex code bases. So why build a separate VM for signature aggregation? Well, this is going to play an important role in the consensus, and so we would like to have perhaps a simpler design that just handles the necessary logic for verifying and aggregating the signatures and ensure small proofs. It's easier to audit. It's easier perhaps to have multiple implementations in different languages. We can also have a design that can be used together with general purpose VM. So I think that it's worthwhile because we have like very tight constraints on what we would like on the signatures, and then it's easier to reason and audit and all that. So as a summary, quantum computers are here and they could break easy cryptography, so we need new primitives. We can have these by using snarks to aggregate these new signatures. And I think that multilinear Starks are a very good candidate because they handle very well sparsity patterns, and we have efficient algorithms to prove memory accesses and all that. A simple VM can be really, really helpful, especially if we want to prove in weak devices and not compromise decentralization. If you want to continue talking, I am here. Thanks a lot for your attention. Arigato gozaimashita.
Thank you very much. ありがとうございました。